Okay, welcome back. I hope everyone is safe and sound and doing well. What I want to do in this video is start material on our next chapter, chapter 10. And chapter 10 is about confidence intervals. And before we get into the details of what confidence intervals are about, it's a good thing to kind of take a little step back and put them in the context of the larger picture of statistics that we've been talking about. So recall that the first step of the big picture of statistics was to form a statistical question. And we know now that forming a statistical question, what it really means is we're answering a question about the value of a parameter. So this is really a question about the value of a parameter. And so it turns out that there are different ways we can address this question, because there are different types of questions we can have about the value of a parameter. Now, this process is called statistical inference. So the method that we use to answer this question is called statistical inference. So this process, what we're doing is we're unable to answer this question directly. Why? Because in order to know the value of the parameter, we have to be able to get data from everyone in the population. And as you found out when you were starting to plan your phase 2 for your project, with a few exceptions, most people had to take a sample. And so what statistical inference means is that we're taking a sample, and you remember what samples do. Samples estimate populations. So we're getting an estimate from the sample. And we're using that to generalize or to make a statement about the value of the parameter from the population. So statistical inference is that huge leap we've been talking about from sample to population. And again, I'll bring up this example that I used before in showing that this is a really huge leap. When we're trying to draw conclusions about the percentage of people that will vote for a particular presidential candidate, the population here that we would have to get the value for that parameter is huge. It's over 150 million people. The samples that we use to get estimates that you hear about every day in the news are on the order of 1,000. So again, thinking in terms of money, right? You've seen $1,000. Very few of us, if any, have seen $150 million. So this leap going from this really small sample in general to this ginormous population is a huge leap. And this is the process of statistical inference. And this, in a sense, is really the beauty of and power of statistics. Now, there are two types of methods that we use to perform statistical inference. The first is called a hypothesis test. And the other is called a confidence interval. These are the two main types of statistical inference that people perform in general. Now, hypothesis tests we are already familiar with, and we know what they do. They let us test to see if a parameter has a specific value. So the purpose of a hypothesis test is that it allows us to test if a parameter has a specific value. And if you go back to when we were talking about hypothesis tests, we gave the three general types of situations in which people have a value that they think the parameter used to be, and they're testing to see if the value has changed in some way, right? So we had, for example, you could use a hypothesis test to test a manufacturer's claim. And so a simple example is, say, Raisin Brands. So the manufacturer of Raisin Bran advertises that there's an average weight in their containers. Okay, so here we have some belief about what the average weight is, maybe, say, 16 ounces. And a consumer group might want to test that the population mean is actually 16 ounces. They would do a hypothesis test. We also considered the situation where there was some sort of change that occurred. So, for example, in some of the homework problems, we talked about motorcycle fatality accident rates. So we used to know what the value was before a law was passed that made helmets optional. And now after that change occurred, after that law is passed, we think that might have affected the population of accidents and might have increased the number of fatalities. And so here we might have some value for what the percentage of people who died before the law was passed. And I don't know, I think I made up a value in this case. Maybe it was 18%, I don't know. And then after the law was passed, there was a change. We might want to see if the population proportion increased, okay? And of course, the last is if we want to test to see if a population has some characteristic, has some property or characteristic. And a really good example of that is our male rat empathy experiment, where we wanted to see if male rats had empathy, the population of male rats were empathetic. We found a way to quantify or measure that, and we wanted to see if the percentage that would open the door exhibit empathetic behavior was greater than 50%. So that was our exact value, okay? We wanted to test to see if the population proportion was greater than 50%. So this is what a hypothesis test does, and hopefully we're all pretty familiar with that now. But it turns out that hypothesis tests are really only half the puzzle. There are a lot of times when we have no idea what the population parameter value could even be, let alone have a specific value that we want to test against. So a classic example of this is, for example, if I ask the question, what percentage of people in Morocco have cell phones? I have no idea. I mean, I would probably guess it's greater than 50%, but it might be a lot greater than 50%. And it might be less. I really don't know. So I don't even have a clue as to what the parameter value is. So there's nothing I'm going to be testing here. There's no value I'm going to be testing. Instead, what I really want to do is I want to estimate the parameter value. So confidence intervals, what they do is they allow us to estimate the value of the parameter. Estimate parameter value. Now, I want to explore what this means a little bit, because it's not so obvious that there's even a need for us to do this, okay? So I'm going to go ahead and erase this, and we're going to talk about why there is a need for us to estimate the parameter value using a confidence interval. It's a little hard with these headphones. I have to be careful how I turn because they're not that, I don't have a lot of slack. Okay, so why do we need a confidence interval? And people sometimes abbreviate it CI, so I'll use that very common abbreviation. Why do we need a confidence interval to estimate our parameter? Okay. And the reason why we're asking this question can be illustrated by a really simple example. So let's suppose as an example, this is the population of Embry-Riddle students here at Daytona Beach. So there's my population, and I might be interested in what percentage of Embry-Riddle students knew somebody who was affected by COVID-19. Okay, so I might want to estimate so I'm going to let pi be equal to the percentage of all Embry-Riddle students who know someone affected by COVID-19. It's an interesting question. What is its value? I have no idea. Okay. Might be very high, but we don't know. So we can't really run a hypothesis test. And you might say, well, just take a sample, compute the sample percentage, and that's your estimate. And so I want to give you a really simple thought experiment as to why that's not a sufficiently good answer. So let's suppose, for example, I want to estimate this, and suppose you do also, and we both take samples, okay? So let's suppose that you take a very large sample, okay? Maybe your sample size is, I don't know, we'll say 4,000 students, okay? So you take a very large percentage of the population, and you get a sample estimate of, and we'll say it's 64%. And I'm just making up numbers. Okay, this is just to kind of make a point. Suppose I, on the other hand, am not as ambitious as you. I take a considerably smaller sample, and let's suppose I take a sample of 25. And we're going to assume, just for the sake of simplicity, these are both random samples. So they're both good samples in that sense, okay? So I take a sample size of 25, and I find out that my sample percentage is, let's say, 52%. Okay. So this is me, and this is you. Are these estimates equally good? In other words, if you had to choose one of these estimates, which one would you choose and why? And I want you to stop for a second and think about that. What is the difference between these two samples? The sample size. And hopefully you said that your estimate would be better than mine. And the logic behind that is, we know that estimates that come from larger samples are more precise. They're less likely to be further away from the actual value. Okay? So if we actually looked, say, at the sampling distribution, right? And let's just suppose the real value, I'm going to plot both of these, okay? Let's suppose the real value is, give me 1 second. Yeah, let's suppose the real value is, say, 65%. This is the actual value. And let's ask ourselves, what would sample percentages look like that came from this population if I took samples of size 4,000? Well, I won't go into a really long calculation, okay? But I could use the central limit theorem, okay? And the central limit theorem would tell us, so this is your observed value, it would tell us that your estimates are going to be really tightly bunched up around 65. Okay. So these are sample percentages, okay? And in this case, if we took random samples of size 4,000, we know large sample size, very precise estimates. Central limit theorem tells us exactly what it is, but we know even without the central limit theorem, it's very, very tight, very, very, very tightly clustered around the actual value. And here's your value right here. Okay. Mine, on the other hand, if you go through some calculation here, you'll find out that the sampling distribution, if you took random samples of size 25, they're going to look more like this. much more spread out, right? So these are pi hats when n was 25. They're not very precise, right? And, excuse me there. And these are going to be the sampling distribution from pi hats when n was 4,000. All right. And you can see very clearly that these two estimates definitely are not of equal quality. Okay. This comes from a population that's much more precise. This is less likely to be further away from the actual value than this is. And so here's the problem. The problem is if we only look at the estimates, so you might step back and say, hey, why do we need to do anything else? We take a sample, we get an estimate, we're done. That's our estimate. And the answer is it's not good enough because it doesn't tell us how good the estimate is. So the problem is that, yes, the sample gives us an estimate. In this case, we're looking at a population proportion, so it gives us pi hat. But this estimate, this single value alone, and this is called a point estimate, by the way, in other words, it's a single point or a single value that best estimates what the parameter value is. Okay, so the sample does give us an estimate, but what it doesn't tell us is it doesn't tell us how precise or how good that estimate is. But it doesn't directly tell us how good. And you remember what we use as a criteria for a good estimate. It's like when you go to an auto body shop, right? When does the guy give you a good estimate? He gives you a good estimate when the value that he gives you, the estimate, is really close to the actual value, right? So this sample estimate alone doesn't tell us how precise the estimate is. So what is the solution to this? Well, this is where the confidence interval comes in. So the solution is we should put a little error bar around these values. This is where we're going with this. So the solution that's not particularly good. So the solution is to put an error bar around our estimate, and this error bar everyone has heard of. It's called the margin of error. That tells how precise our estimate is. Okay? And when we do this, this is what gives us our confidence interval. So if we go back to these two examples, okay, we're going to see later on how to calculate this. I can do it in my head because I know a little trick that I'll show you guys later on. But if we go back to this for a second, okay? It's going to turn out that for my case, my margin of error, when you use a sample size of 4,000, the margin of error is 2.5%. So my margin of error is 2.5%. So what that means is I'm going to go to 64. This is actually you in this case. This wasn't me. This was your sample. Okay? And I'm going to put a little error bar of 2.5% on both sides. So now this, if I add 2.5 to 64, this is 66.5%. And if I subtract 2.5%, this is 61.5%. And this is your confidence interval, okay? So your confidence interval is going to be 61.5% to 66.5%. So notice what we've done. First of all, let's kind of explain what this means. What we're doing now is we're not giving a point estimate for our parameter value. We're giving what's called an interval estimate. In other words, I'm estimating the range of values that the parameter could actually take on. So this means that you believe the true percentage, pi, is somewhere between 61.5 and 66.5. You're confident. And we're going to talk about what confidence means precisely, but this is the idea. That you think or you believe or you're confident that pi is in here. So I'm estimating the interval, the range of values the parameter could have. Now on the other hand, in my case, using this little trick that I'll show you later, you can show that this margin of error is 10%. In other words, my estimate's much more imprecise. I have to put an error bar of 10% on both sides. Okay, so if I do that, well, my value was 52%. It was way down here, right? So it's going to go all the way up to 62%. And all the way down to 42%. Okay? So my confidence interval is going to go from 42% to 62%. And so what I'm saying is I'm confident that the true percentage, pi, is between 42 and 62%. Now notice something. I'm wrong in my case, aren't I? Because the actual value, we know if we were an omniscient being, the actual value is 65%. So this comes into the confidence part. We're going to talk about this later. Confidence intervals can be wrong. The confidence is going to refer to the percentage of time the method works, i.e. the percentage of times that the interval we've estimated actually contains the true parameter value. And we're going to come back to this, okay? So the thing that I really want to emphasize here is that confidence intervals are interval estimates. The take home here is that confidence intervals are interval estimates. In other words, we want to estimate the range of values that we think the parameter can take on. All right, we're going to come back in the next video and we're going to talk about how did I get these particular errors for the margin of error, how did I get those numbers, what is the logic behind how a confidence interval works, and not surprisingly, The mathematical basis for that is going to be the same as for a hypothesis test, i.e. the central limit theorem. And this shows you why the central limit theorem is the workhorse of statistics. Both of the main types of inference, hypothesis tests, and we're going to see in the next video, confidence intervals, are totally based on the central limit theorem. Okay.